So now we're looking at a situation where instead of torque being dependent on theta, it's dependent on time. So again, we always want to look and see which is it dependent on. That will decide which path I take. So this example says an electric motor delivers a torque defined by a function of 5.2 t. So the fact that I'm getting a function for torque means I can either go with this angular momentum way, or I can go with my motion in Newton's second law way. Where the torque is in Newton meters and time is in seconds, the torque is delivered to a uniform disk about an axis perpendicular through its center. The disk has a mass of 3.6 kilograms and a diameter of 0.24 meters. What is the angular velocity of the disk at t equals 1.6 seconds if it starts from rest? Okay, so we are going to be going ahead and using this. So they are giving me a time frame. They're asking me for final velocity. I like the angular momentum method as opposed to getting an alpha equation, then taking my integral to get a velocity equation. So I'm just going to go straight to here. So I have a change in angular momentum is going to be the integral for the first 1.6 seconds of my time, my equation, which was 5.2 t dt. Now change in angular momentum, so that's going to be final minus initial, so I prime omega prime minus I omega is equal to the integral of this. It does start at rest, so all of that is 0. The I does not change, so I don't need that prime on my I. And so to find omega prime, I'm just going to be dividing that I over. All right, so omega prime is then going to be the integral from 0 to 1.6 of 5.2 t dt, all divided by 1/2 times the mass, which was 3.6, times the radius, 0.12 squared. Type this in my calculator. We should get something like 256.8 radians per second. We will have direction on stuff like this, so this would be in the same direction as this torque was being applied, so whatever this direction was will be the direction for that.